Hey folks, we're back again. I'm going to talk about the third part of our partial fraction section today. I've given an example here. Our topic is irreducible quadratic factors. Right, and so as we've seen when we're looking at the denominator of these things, so we're looking at integrating polynomials divided by polynomials, so rational functions, and it comes down to factorizing the denominator, so factorizing the q down here. And everything we've seen so far has had a denominator that's completely factorizable into linear terms. And by linear, I mean things like, x plus 1 and 3x minus 5. Those are linear terms. But not everything can be factorized. For example, the term x squared plus 1 can't be factorized because, well, think about the zeros. To factorize, I'm looking for zeros, right? This has a 0, the 0 is minus 1. This term has a 0 of 5/3. What's the 0 here? Well, x squared plus 1 has to equal 0, so x squared is equal to minus 1. There's no real number that when you square it, you get minus 1. So there is no way to continue factorizing this quadratic in the real numbers. You can factorize them in the quadratic numbers, in the complex numbers. I could say that x is plus or minus the square root of I, but we don't want to resort to complex numbers right now. So the fact that I'm leading to a non-real number here means that it's an irreducible quadratic. This thing here is an irreducible quadratic, and in this case we see that x squared plus 4 is an irreducible. So we can't factor it anymore, so our rules don't apply, so we need a new rule, and here's our new rule. And so we see this has some similarity with our previous example, where we had to take every possible power up to and including the highest power that we saw in the denominator. In our example here, the power is a maximum of 1, and so we're only going to be looking at this first term. But if this was a 4, then I'd have a to the power of 1 and a power of 2, or to the power of 3 and a power of 4 included. So in this particular example, when I've got x squared plus 4, the terms we're going to gather are going to have an x squared plus 4 in the denominator. And what's new is the linear nature of the term in the numerator. So writing that out, what we're going to find is, and actually now that I look at this I realize I've made a typo, so I'm just going to make this a plus 1 up there, and then an x squared plus 4 in the denominator, and then we're going to use this rule. Well, to begin with, this is a proper fraction, proper partial fraction, so I'm just going to get some constant over x plus 1. I know that's going to appear because that's what we've been talking about up to this point anyway. What's new is what we do with this irreducible factor. It's irreducible, again, because there are no solutions to this. There are no x values. There are no x values that make this thing 0 that are real. There are imaginary values, but there are no real values. And so our rule says we need an irreducible in the denominator, but then a linear term on top. So I'm going to call this b and c. The whole idea is A1 and B1, A2 and B2 are just using these symbols to give us a way of writing it in the general case. It just says I need something linear on top, a number multiplying the x, and then a constant. Right? And then, once we've got this form, the entire thing that's new is this form. Once we've got that form, we just put everything back over a common denominator, and we can use the idea that we had last time to solve for A, B, and C. Now it's going to be a little more complicated this time because of the form of the denominator or the factors there, and we'll see that when we work the problem in a second. But just putting that whole thing together, sorry I lost the 4 there, putting this whole thing together, when you see again I've designed it so the x squared plus 4 and the x squared plus 4 cancel, and I'm left with a over x plus 1, right? Or similarly the what have I got? X plus 1 and the x plus 1 cancel. I'm left with bx plus c over. So hopefully you see that that's the right form of common denominator. And now what we're going to do is use this to solve for a, b, and c by comparing the numerator on the left here with the numerator on the right. And when we put all that together, we get this condition that x squared plus 1 has to equal this combination of terms. So let's go on the next page and actually work through solving this problem. And so here we see the original integral, and then we have split that up into partial fractions. This is the partial fraction decomposition. It's the best we can do with irreducible factors. The fact that x squared plus 4 doesn't decompose anymore, can't be factored anymore, means this is the best we can do. And so when we looked at the the numerators, we came up with this condition. And now let's go through and check that condition for certain values. The simple one to start with is when x equals minus 1, because that'll make this factor 0. And that'll leave us with minus 1 squared is 1, so 2 on the left, and I think that's going to be 5a, so plugging minus 1 in there, squaring it, you get 1 plus 4, that's 5. 5a plus, and everything else is going to drop out, right? Because x plus 1 is 0. So this whole last term is 0, so we know a, it's 2/5. All right, so let's try another value. And there are no zeros for x squared plus 4, right? Because the whole point of this being an irreducible is that x squared plus 4 is never equal to 0 for any real number, for any real value of x. That's where we started with this problem. So there's no easy value in a sense to plug in here, so the easiest may be just starting with 0. And if I plug in 0, I get 1 is equal to 4a, is that right? Plus, well, the b is going to drop out, so we're going to be left with c. There we go. And so c is 1 minus 4a, and a is 2/5. So what's this? 1 minus 8/5, that's minus 3/5. And so there's our value for c. Now last job is to find b. And again, we just need to pick some value. So maybe another easy value to pick is 1. I'm just picking numbers where the algebra is easy. Because in this case, we get 2 equals, plugging x equals 1 in here, again, 2 is equal to 5a, and then I've got this mess in here. X is 1, right? So this is plus b plus c all multiplied by 2. Now the nice thing is we know that 5a is equal to 2, so we know they cancel. I can plug a in, they cancel, and we're left with b plus c is equal to 2, which means b is minus c, which is 3/5. So there's a value for b. And now we can put the total integral together. And when we do put that together, just plugging the a and the b and the c in, we end up with this thing. And this is hopefully not too hard to integrate, I hope. Let's look at it for a sec. I'm going to write this as 3 separate integrals, because this is the integral of 1 over x plus 1 multiplied by 2/5. And then there's 2 other integrals. In this case, it would be smart if I split them up, because the first one is x dx over x squared plus 4. And then the second one is not x dx, it's just, let me make some room here. I'm going to pull all of this over there a little bit. This is just dx over x squared plus 4. So there's 3 integrals. There's the piece coming from here, and then there's the piece that's coming from bx over that square root, and then there's the piece that's coming from the green part. So here's the green part. It's just literally minus 3/5 over that irreducible quadratic, and then the other piece is 3/5 x over that irreducible quadratic. And they're very different. We're going to do them in different ways. We know how to integrate the first one, right? The first one's pretty straightforward because we've done that a lot at this point. That's the natural log of the absolute value of x plus 1. There's the integral of this. The next one, you might not immediately realize, but if you look at it for a second, hopefully you'll see that this is a u substitution. U is equal to x squared plus 4. du is 2x dx. And so when you do that, you're going to end up with a factor of a half out the front. And what you're going to end up with is 3/10 of, this becomes du over u, right? Literally I can put a half there and a 2 there. So now this is du over u. Du over u is log u. So this is 3/10 the natural log of u, which in this case is x squared plus 4. If you can't see that immediately, do that u substitution, but we've done problems like that before in the course. And the last one is beautiful because the last one is an inverse tan. And before I complete it, let's go on the next page and look at it for a sec. Right, this is an inverse tan, And if you remember how inverse tans work, we have this nice formula for inverse tans. And let's generalize that a little bit to the integral of x squared plus a squared. Because remember, I can write that like this. I can factor out that a squared. So I can write this as x over a all squared plus 1, and then I'm going to put the a squared there. So I've just done a bit of algebra on it. Doesn't look very clear here. But so this is a 1 over a squared, the integral of dx over, and I'm going to call this u. So we're going to put u equal to x over a, and then we can work out du. Du is dx over a. So another way of saying that is dx is equal to a times du. And so I can rewrite this thing, which right now looks like this. I can rewrite it as 1 over a squared, the integral of, well, dx is a du, and then we're left with on the bottom u squared plus 1. Now one of those u's cancel. You can see, I hope that u and that a and that a cancel. And so what we're left with here is 1 over a, and then the integral of 1 over, well, basically this integral with u's instead of x's. And so that turns into the inverse tan of u, which is x over a, plus a constant. So I did that quickly down there. I'm going to take this now as a formula that I know and that I know how to derive, and I'm never going to derive it again because I'm just going to use it. And this is something you should remember. The integral of 1 over x squared plus a squared is an inverse tan integral. It's 1 over a inverse tan of x over a plus a constant. And if we remember that rather than deriving it every time, it'll save us some time. Because that lets us work this integral out, right? Because it's 3/5, and a squared here is 4. So a is 2. And so this is 3/5 of that integral is, well, 1 over a, 1 over 2, inverse tan of x over a, x over 2, plus a constant. And so there's the integral of that one piece. And now I'm just going to go back and put that piece literally into our answer on the previous page. So let's go back. And I'm just going to write that down. Right, there's the thing we just derived. It's 3/5 times a half the inverse tan of x over 2, plus a constant. And there's the integral in this case. And this one's pretty typical of what we're going to see for all of these kind of integrals that lead to irreducible functions in the bottom, irreducible quadratics. We're going to end up with terms that come from the other, terms from the other things, so from the x plus 1 in this case. But then we're generally going to end up with a bx plus c. Right? We're going to generally end up with a term that is x over x squared plus a squared, and that's going to lead to a log of the square. And then we're going to end up with a term that's 1 over x squared plus a squared, and that's going to lead to an inverse tan. So this is really typical of the kind of things we can see. Let's have a look at another one. Alrighty, here's another one. This time we've got an irreducible quadratic, x squared plus 1. You can always tell it's irreducible by just looking at the zeros. And there is no positive number, there is no real number x where the square of it is negative. So there's no solutions to this that are real numbers anyway. So we know that's irreducible, so we know we've got to use the rules that we've just discussed. And the fact that we've got to use the rules we've just discussed means looking at the linear factors that are distinct. In this case, there's just the x minus 3. And then the repeated, in this case, irreducible quadratic, which is going to give us a term that has x squared plus 1 in the denominator, and then another term that has x squared plus 1 all squared in the denominator. And in the numerator, we've got to put linear terms. So I've already used a, so let's call this bx plus c, and this one dx plus e. All right, so our job is just to find a, b, c, d, and e, and that looks easier than it is. Let's have a look at the algebra. The first step with all of these is always to put them over the common denominator again. And so the way I think about it is look at the term we've got. So for example, look at this term. What's it missing? If I want the common denominator to be x minus 3 times this thing squared, then this is missing a factor of that squared on the bottom. So I multiply by x squared plus 1 all squared, top and bottom, and I pick up that term. Something similar is going to happen in the next term. In this case, we've got a bx plus c. Now, comparing to the denominator I want, I don't have an x minus 3, so I've got to multiply that top and bottom here. And I'm also missing a power of the x squared plus 1, so I need a factor of that as well. Right? And again, remember that the point here is that I can then say, ooh, cancel all that, cancel that and one of those, and what I'm left with is what I had there. That's how I built it. That's why I built it. So let's get rid of all of that messiness. But what we have is one more term, and that last term is the dx plus e, and that's got to be multiplied by, well, what do you reckon? If I look at dx plus e, it's already got this piece in the denominator, so what it's missing is the x minus 3. All right, and so what we've got here as a total result is all of this stuff. Let's move it down here. It must equal the denominator over there, which was 100x. Oops, what did I do to the 100x? Let's move the 100x over here and then fix the things I just broke. That's a plus 1, and that's an equal sign. So that's the numerators, right? The numerator is 100x on one side, and on the other side it is that horrible mess. We've got to solve for A, B, C, D, and E, and the easiest thing to begin with is to just look at the x minus 3 term again and say, let's put x equal to 3 and see what happens. When I do, on the left I get 300, because it's 3 times 100. That term does not cancel, but this one does, and that one does. So all we're left with is A times 3 squared plus 1 all squared. 3 squared is 9, plus 1 is 10, so this is 10 squared, or 100a. And so we know immediately that a is equal to what? 3. Unfortunately, that's the only one of these that's easy to work out. The rest of them are going to be a mess. So let's go to the next page and see what we've got. In the previous example, we could plug in special values and make progress. You can try that here. It'll certainly work, but it's going to leave you with disgusting equations. So that actually, when they get this complicated, the best approach, it's not pretty, but the best approach is just to multiply the whole thing out and then look at corresponding powers. Because already, if we look at the left, there are no x cubes, there are no x squareds, there are no x to the 4s. And so the coefficients of those terms all have to be 0. Because I'm going to pick up x squareds and 4s over here. But in the end, I'm not going to get any of them. So I'm going to have to take the coefficient, set it to 0. Let me start writing this out and we'll see what I mean. So I'm literally just going to start multiplying this out. This is x squared plus 1, all squared. When I square it, I get x to the 4 plus 2x squared plus 1. If that's not clear, multiply it out. The next one's not as clear, but think about it this way. Whatever this product is, it goes there and there. Whatever that product is in red, it's going to multiply the bx. Here it is multiplying the bx. And it's going to multiply the c. Here it is multiplying the c. And so when I do multiply this thing out, I'm going to get x cubed. Those two terms are getting x cubed. I'm going to get minus 3x squared. These two terms will give that. Then I'll get a plus x, and then a minus 3. And you can almost fit that in there. And so I'm going to get that same term on the other side. So let me just get rid of that bracket for a second. I'm going to get that same term there. There we go. So in red, what I've got underlined in red is just what's coming out of this product, and then I'm multiplying it by bx, and then I'm multiplying it by c. And then the last two terms, this, again, foiling this out, I'm just writing it out. I'm going to get a dx squared, I'm going to get an ex, I'm going to get a minus 3dx, and we're going to get a minus 3e. My job now is actually to split it up with powers. So all of the things that involve x to the 4, what do we've got? We've got one here. There's an a times x to the 4. This term here is a x to the 4. And there's a b x to the 4 there. So I'm going to have an a x to the 4 and a b x to the 4. And that takes care of that term and that term. And I'm just going to go through and collect all of the x cubes now. There are no other x to the 4s. So now I'm going to look at x cubed. There are no x cubes in this section. There's one here, because remember I'm multiplying this x by that x. So I'm going to get minus 3b x cubed from that term. So let's mark it off. And then I'm going to get over here a c x cubed from this term. And then there are no more x cubes that I see. So that's the end of the x cubes. Now let's look at the x squareds. When I look at the x squareds, I'm going to get 2a x squared out of that. So I'm going to write that one down and mark it off. 2a x squared is done. Here there is going to be a b x times x, so a bx squared. So I'm going to add on, I think, the b there. And then what else have I got? There's going to be an x squared here, minus 3c x squared, minus 3c x squared is this term. And then there's going to be a d x squared. And I think that's the end of the x squareds. There's the dx squared. And then what about the x's? Well, then there's going to be some x's. Looking in this term, there are none. Looking in this term, there's going to be minus 3b times x. And so that's the last term there dealt with, the minus 3 times the b times the x. Here there's going to be a plus c times the x, so adding that on. And over here, I think there are two of them. There's going to be the minus 3d times x, and there's going to be the e times x. Order doesn't matter, but there's a minus 3d, and then there's the e. The last one is just the constants, so just the multiples of 1. There's going to be a times 1 over here. In this term, I get minus 3 times c, so that's actually minus 3 times c. That's coming from this term, so let's mark those off. That one, and then the last one is minus 3e. Is that right? Yeah, minus 3e, minus 3e. And all of that has to be 100x. And so what I can do is compare the coefficients of x to the 4. When I look on the left here, I have no x to the 4s, so I'm going to write 0. But when I look on the right, I've got a plus b x to the 4s. When I look at the x cubes, what I'm going to find is on the left I have none of them, and on the right I have minus 3b plus c of them. I'm literally just saying the coefficients have to be the same. That number must be equal to the number of x cubes I have on that side, which was none of them. And then I'm going to look at the x squared. Now I'm going to do this for every single term. I'm going to do it for the x's. I'm going to do it for the 1s. When I do it for the x squareds, I've got no x squareds. When I do it for the x's, I've got 100 x's. And when I do it for the 1s, well, I've got no 1s. All right, so there's the left. Looking at the right, for the x squareds, this is a 2a plus b minus 3c plus d. That's that quantity. When I look at the x's, it's minus 3b plus c minus 3d plus e. And when I do it for the 1s, that's a minus 3c minus 3e. Oh, and remember, we already found what a was. So we know that a is 3. And that's good to know, because then I can use this information over here to say that b is minus a, so it must be minus 3. I have now solved for b. Right? And if that's not a very clear, let me change colors because that maybe is a bit dark. Let's make this one blue. We've now got the value of b. So we know a and b. So this next one we can use to solve c, right? Because c is equal to 3b. And b is minus 3, so this turns out to be minus 9. There's our value for b. And if I know a and b and c, then I can use this equation for d. d is what? 3c minus b minus 2a. 3c is what? Negative 27. Subtract b, well, that's the same as adding 9. Subtract b is the same as adding 3. And then subtracting 2a is subtracting 6. Minus, that's meant to be a minus 6. And I think that whole mess works out to be minus 30. So there's a value for d. And then I can use, well, maybe I can use this one to find e. E is 1/3 of, what would it be? A minus 3c. A minus 3c. And this is 1/3 of a is 3. And this becomes plus 27. So this is 1/3 of 30. So it's 10. And if you plug that value into the one I ignored, because it looked like more work, you'll find it's satisfied as well. If it's not satisfied, we've done something wrong. But we've used each of these equations to find a, b, c, d, and e. Are you as tired as I am? Let's put all of this together. Okay, so we found all the constants. Here they are. I just put them in a table. This is the expression we started with. A over x minus 3, well, that's 3 over x minus 3. And then the b, this is going to be minus 3x plus c. I didn't write c down. C is minus 9, so this is going to be minus 9, all divided by x squared plus 1. And the last term is d, and d was minus 30 plus, dx plus e, and e is 10, all divided by the square of that irreducible quadratic. Whew. So with that information, we can set up the integral. And here it is. And we can integrate some of that immediately. The first one's easy, so I'm just going to write it down. That's 3 times the natural log of the absolute value of x minus 3. Just doing that first integral. This second one breaks into 2 pieces, so let me write them both down. I can write this as minus 3, in fact let's get rid of that, minus 3 times the integral of x over x squared plus 1 dx, and then there's going to be the minus 9 times just the integral of x squared plus 1. So both of those are coming out of here. Right? So I'm looking at this term and it's producing these two. This one's a u substitution, this one's an inverse tan. What we've got in the next one though is we're going to have minus 30, and this is going to be x dx over x squared plus 1 all squared, and then plus, I think, was it plus? It was plus. And then we're going to have plus 10, the integral of just 1 over, so just dx over x squared plus 1 all squared. So those last two, again, are coming from this split into 2 pieces. There's the minus 30x, and then there's this. The reason I'm splitting them into pieces is because they're done differently. Right? These are the kind of problems we've been doing. This is the absolute value of x minus 3 again. And now, this one, well, if I put a 2x there and a half there to cancel it, this is just a simple u substitution. If you put u equal x squared plus 1, then du is 2x dx, and that's du over u. So this is the kind of integral we've been doing. So this is 3 halves. Do the u substitution, but you'll get this. 3 halves, the natural log of x squared plus 1. The next one, though, is not a u substitution. It's an inverse tan. And a squared is 1 in this case. So this is inverse tan with a squared equals 1. And so just using what we used in the previous example, this is going to be 1 over the inverse tan of x over 1. So there we go. There's that second one. That's coming from here. That one's coming from there. The next one is also a u substitution, because I can put a 2 there and a 2 there, and now the same substitution, x squared plus 1, this is the integral of u squared. Right, if I go up here a little bit, let's think about this. With the substitution x squared plus 1, du is 2x dx, and so that integral becomes du over u squared. And that, the integral of that is minus 1 over u. Well, I know what u is. So this is 1, this becomes minus. So there's the 30 halves floating around, multiplied by 1 over u, so 1 over x squared plus 1. Beautiful. The next one is a little harder. So what I'm going to do is take this one and go on to the next page and work on it separately. And then we'll come back. Looking at this one, it may not be immediately obvious, but this is a trig substitution. This is a trig substitution that's going to take advantage of the identity. Tan squared theta plus 1 is equal to secant squared theta. We're going to make the or the x substitution in this case. We're going to make the substitution x is tan theta, and then dx is secant squared theta, d theta. And then the last piece that we want here is the x squared plus 1. Well, that's tan squared plus 1. And the idea of doing this in the first place is that that's just secant squared. So substituting all of that back in, we're going to get the integral of dx. Well, dx is secant squared theta d theta. This is good practice for the previous section, right? And in the denominator, we're going to get x squared plus 1. Well, that's secant squared. So this is secant squared theta, but that's a squared. And so we've got 4 secants on the bottom, 2 on the top. So it's 1 over secant squared. so it's the same as cosine squared. All right, so we're going to end up with the integral of cosine squared. Do the algebra of that, it's 1 over secant squared, which is cosine squared. And now to do that, we use that identity, right? Cosine squared is a half of 1 plus cosine 2 theta, d theta. And so we need to integrate that. So this is going to give us 1/2 of theta plus 1/2 of sine of 2 theta plus a constant. We don't care about the constant, we're going to put it back in the other one. But before we do, we need to use a triangle. We know what theta is. From this top piece, x is tan theta, so theta is just the inverse tan of x. So the first one's easy. This is 1/2 the inverse tan of x plus, well, this we need to use a triangle for. So if I draw my triangle down here, here's the triangle, right angle, theta. And what we started with was tan theta equals x over 1. Right? And tan is SOHCAHTOA, so opposite is x and adjacent is 1. So this is the square root of x squared plus 1 squared. All right? And that gives us the two pieces we need, because, let me rewrite this one more time, sine of 2 theta using a double angle formula is twice sine theta cosine theta. And so what we need is sine theta and cosine theta. So putting this all together, we're going to have the inverse tan of x, the half and the 2 cancel. Sine theta is opposite over the hypotenuse, right? SOHCAHTOA. So opposite is x, so this is x over the square root. And cosine theta is adjacent, and adjacent is 1 over the square root. And so when I multiply those two things together, I'm going to get these, the 2 and the half cancel. When I multiply them together, I'm going to get x over x squared plus 1, because the square roots are going to cancel, plus c. Whew! And so this is our answer for that last piece of the integral. So let's go back, see if I've got room, and I'm going to paste it in there. And then, I forgot to add a c. Okay, and that's our final integral. That whole last piece that I just did on the separate page, that was just integrating this. And it shows you that sometimes your integration's going to end up going back to trig substitutions. It's going to go back to U substitutions. It's going to go back to these things we haven't that we've seen before. There's a lot in some of these problems. Rest assured, I'm not going to give you a question on a test that asks you to do every one of them at once, but I might ask you a question that gets you to do all of the individual pieces. And certainly on the web work, you've got time to work on a lot of the individual, a lot of more complicated problems like this. So I hope that gives you some idea of the fun that we have with these integrations by partial fractions, because it really leads to a lot. But remember, a lot of what we've done is just algebra. A lot of what the work in this is just solving some algebraic equations. All right. As you study these things, as you think about how these might be asked on a test and a quiz, I'm certainly going to ask you to solve the algebraic equations. But notice that everything I did could be done on that expression, right? Because the a's and the b's, they just kind of float around out the front. So I could ask you to do this integral, do these integrals, without finding the a's and b's, because you end up with everything except the number out the front. You could just write it as an a. So that's the kind of thing I might ask on a quiz. Have a go at some of these, especially the initial ones. It's really important to practice these, and then come and ask me in office hours and we can sort out issues you might have. Have a wonderful day.